Hello, everyone. So, that's a little teaser at the cover I have set up for this weekend. I will be announcing what the name of that song is and the band that plays it originally at the end of this stream. But today's stream is dedicated to the AI, which is something I haven't been able to say for, I want to say, a couple weeks now. I haven't been able to get a lot of work done just based on the fact that I had a lot of tests going on. And at the same time, I had kind of hit a wall. I had some ideas, but I didn't really know where to move forward with the data mining project that I was working on. But one of those ideas ended up being what I moved forward with. So you may have heard a little bit of what I'm going to talk about here today, but I want to also talk a little bit about how I will be applying these changes into the future. And so I actually should have prepared a little bit more before I started this because I want to be able to show you the work I have done, but we'll get to that when I finish introducing the ideas. Also, on a general note, I am doing No Shave November. I don't know if I mentioned that on the Q&A stream that we had on the weekend with my girlfriend, but it is halfway through the month, so you can see it's starting to become visible on the poor quality of my laptop webcam. So I just want to thank you guys for coming out if you're watching live, and if you're watching late, thank you as well. But we're going to get right into the topic. So I'll pull up a paint window just in case I need it. But generally, the idea that I am about to talk to you about is the idea that I've actually sort of cracked the data mining project. So if you are keeping up to date with my projects, or specifically with the data mining project, you'll know that I kind of hit a wall in the data mining because I was attempting to use the iterative methods like steepest descent and Newton-Raphson to quickly find the optimal arrangement of equation pieces in order to sort of take out the evolutionary process, because the evolutionary process is very slow, although it's very powerful. Now, the evolutionary neural network will still be there, so don't worry if you're a big fan of neural networks. It's just going to have a little bit less of a role in the actual creation of the equations. It will essentially be creating the environment for which the optimal equation can be created. So what I want to I'll try and illustrate this, I guess. So essentially, before, what was happening was that we had the neural network over here, and we had the deep learning over here, and that was it. And so what was happening was the neural network was a genetic neural network, and so it would go one iteration, it would create some population, and as it created that population, random mutations would occur. So essentially, what was happening was that these random mutations had a chance to either just change with a trait that was already known, or to have a deep learning trait be added in. And so what a deep learning trait is, so if we had our inputs X, Y, and Z, deep learning could create an association, a random association at that is, I don't know, Y plus Z. Now, this wouldn't be too significant because it'd be fairly easy for a equation to be Y plus Z. But as the deep learning continues, this is now an option. So in the next generation, if this were helpful in creating a better equation, then the deep learning aspect of the program would then have this as an option for a single trait, which could then be given in associations with other traits. So the equation could become complex in its individual parts, along with growing in a linear combination. And so this was a very powerful method, but at the same time, it wasn't fast enough and it wasn't efficient enough. So the problem was I had run this several times with different parameters, adjusting numbers here and there. But overall, I kind of just needed to scrap the whole thing because it was only successful once. It got somewhat close a couple other times. And what I mean by somewhat close is I created a set of data that was all based off of one equation. There was no error whatsoever. So essentially, there was a chance that the AI could find the answer. And so this is something that doesn't necessarily happen in real life, but in terms of adjusting a method in order to create an efficient process, it's important to try the easier processes. Maybe not in every case, but it's important to make sure that you can get each baby step. So sometimes that doesn't necessarily get you where you need to go, but for this situation, taking baby steps was important because it made sure that the code was running correctly while that was happening along each step. So what am I doing different from this? Well, we still have deep learning, so I'm going to clean this up. We still have deep learning, and we still have the neural network, like I said. And there's still a genetic aspect to it, but what I'm adding in is a extra little piece of the puzzle here. So what this is the optimizer. And now I've talked about optimizers in the past as a sort of second gear, but in this case, it really is first gear. So what's essentially happening is that uh, the genetic neural network, all it has control over is one thing: the length of the equation. And so what I mean by that is all of the equations created by the neural network will be a linear combination that is added together. So that's significant. Everything is just plus signs. So all this neural network is deciding is how many pieces there's going to be in the equation. Where those pieces come from, well, there's the initial inputs x, y, z, dot, 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 and there's the inputs created by the deep learning. So essentially, deep learning is doing the exact same thing that it was before, but to an extent. So essentially, what I'm going to be doing differently this time is instead of random mutations, every single generation, I will just simply call the mutation function and get a population of new mutations to be thrown into the pool of possibility. So if you've been keeping up to date with this channel, the way I'm handling deep learning is essentially I'm keeping, there's a deep temp list and there's a deep list. So all of the inputs are immediately onto the deep list. So they're not even in the file that has all of the variables. They're just assumed because they're just the data point, and that's pretty easy to bring up. There's no associations that need to happen. But what happens is every generation there's going to be, I don't know, let's say 20%, a 20% increase, or that might not be true. Let's just say it creates I don't know, 20 new variables. That might be a lot, but we'll see. We'll see. I gotta actually finish the coding and then mess around with the numbers once we get there. But essentially, the new population per se is going to be all of the new toys that the optimizer has to play around with. And so this is actually something I've been debating, whether or not a genetic neural net should be the decider of the length, or if it should just be thrown out altogether. Because what I can do if I throw it out altogether is I can just try the 10 lengths close to the current length we're at. And if it ends up finding that it needs to be longer than or shorter, then it can just jump to that point as opposed to randomly selecting it. I don't know which one will be faster because let's say the equation needs 100 terms and we're at 1, then it won't really jump there. But at the same time, neither will the neural network. So I'm kind of leaning towards the idea of just throwing it out right now. But you guys can leave comments on how you feel about that. I have the chat up over to my side, so if I'm looking over there, that means I'm looking at the chat to see if there's any questions. So essentially, let's just act like I've already removed this. So what this would mean is that every every generation, the um, the the deep learning will create a new population of temporary equation pieces. So there's 12 there. So these all get put on the temp list. And what that means is that for this generation, they are available for use in the optimizer. And what the optimizer is essentially, I've explained this in the past, but I'll give a quick description. So what's happening is I'm using a steepest descent algorithm, and I'm going to explain how it's a little bit different from the normal steepest descent linear regression. But essentially, what I realized is that if you take the values of the equation pieces when you plug in the data points, so say this has x plus y all divided by z, then and that's in this spot. Then what you can do is you can plug them in for a specific point, and you can sort them in ascending order. And what sorting them in ascending order allows you to do is set up a step function, and you can use steepest descent to create these piece selectors, so A1, A2, A3, and these will be what goes in here. And so if this value rounds to a 1, then it would be the first term. Well, if you're in computer programming, that would actually just be the 0th term. So if it rounds down to 0, then it would be the first term. And so this would get plugged in, and its value is constant for that data point. So what that allows you to do is that the steepest descent algorithm can march up and down this step function in order to find the final value that it needs. And so I'm just gonna clean the slate since I'm on the topic and talk about the optimizer, and then we'll get back to how that applies into the full AI. So we have our optimizer. I'm just putting it as a triangle. I don't know if that's meaningful for anything. I know triangles mean change or delta. So what the optimizer is doing is this is a steepest descent optimizer, and steepest descent means that it looks at the gradient of the function that I have presented it, and it moves down the gradient. So if we had a function that's like this, then and we gave it at this point, it would look and say this is the quickest way up, so it's going to take a step in this direction, a tiny step. And so it's going to keep taking baby steps. And the problem with steepest descent is it'll actually get stuck here. But if you have a nice curve like this, that's not a problem. There's no holes. It will just go all the way down to 0. And actually, what I needed to do was in the actual evaluation, the essentially what's happening is for the sorting function, let me clean this up. For sorting purposes, there was it just puts them in ascending order. There's no absolute value or anything. But when it comes to the actual evaluation, in order to approximate the derivative of the function we're looking at isn't this step function that we have that I was talking about. It's actually the linear combination of all of the equation pieces. So if we have 4 pieces, so that would mean that A can range from 0 to 3 in index values, then essentially this is a 4-dimensional problem. And so that might be a little hard to grasp. So let's break this down to just a three-dimensional problem and say that there's two values. Well, a three-dimensional problem will look a little bit like this. And so you can imagine that this is actually straight out of the screen. And there may be some function that looks kind of like this, where there's this weird plane, and you can imagine that this is extending out in that direction. And and so it kind of makes this cup. And so what this means, and the reason that it does this is because I've actually set it up so that and so this point's actually supposed to be 0, so that's kind of important. But what I'm doing is that this is the function of a0 plus a1 plus a2, and all of these a's can be all of these a's are functions of the data points, but these a's are the step functions. So it's three of the same step functions essentially. And what this essentially is doing is it's trying to find, or actually it's this minus the final value. So this is some we're just going to call it big F. So this is our function we're trying to approximate. So the value of the function at the given data point. So it sets up the step functions, and then it subtracts out the function. And this is all absolute value. So what it does is any point that is not on the exact point that is the true value of our function is actually a positive number. And so we can use our steepest descent to crawl slowly downwards until we hit the lowest number possible in this situation for an absolute value function that's 0. So that's what's going on with steepest descent. And now, I did talk to you guys about a problem with these iterative methods. And so what that problem was that what's happening when we have a full data set is that we want to find the line that best fits the data. And so if we had some scatter plot and an axis, then you might say that there's a line that goes through there. Now, you can use steepest descent to find this by taking the data points, taking the y values of the data points, so f of x. And so what you do is you do the least squared regression. So you essentially find the sum of all of the data points minus what they actually are. So how far off they are from this function we're approximating. So all of the points we're approximating, so here, 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 on this line would go in here. And then all the actual data points would go in here. You square this, and this sum is your fitness score, essentially. The reason this works is similar to the absolute value because there is this squared term, so all of the values will be positive if they are not 0. So the way that works is it measures the distance between this. Now, the way that I'm doing this is I'm not using physical data points to approximate an equation. I'm looking at how the pieces of an equation that I've approximated look in terms of the actual data. So if we had some data that was a sine function, right? And that's not exactly the line. So let's just say our data is just a line at some arbitrary value. And we try to approximate it with a sine function. Well, you can see that there's some error there, and that's not a perfect drawing, but there's some positive error, there's some negative error. Now, if in my model, I can linearly combine pieces of equations. So if I have sine of x, and I have negative sine of x, then it's gonna add together to be um, it's gonna add together to be our value, assuming that these add together at the right point to our arbitrary number. But what the function will see is that both of these have equal um, error from the actual number we're looking for. So it doesn't really work out in the steepest descent function, because the steepest descent function doesn't know how to find this and say this is the correct answer. The reason that it works with one data point is because at here and at here, there's obvious negative error for this and positive error for this. So it can see that if it grabs the positive value, the sign of x, then it'll get a positive value. And if it grabs the negative sign of x, it'll get a negative value, and those will cancel out to equal the number that we're trying to find. And this all works out because of this multi-dimensional plane that's set up in order for there to be a gradient that the steepest descent algorithm can go down. So that's essentially what I'm doing. Is I'm taking a sample of the points, in this case 100, which seems to be relatively enough to work in my case, but that might need to be larger in the future. And what I'm doing is at each point, I'm finding what the optimal equation is for the given amount of pieces that I'm allowing it to play with, and the physical pieces that I'm allowing it to play with. So remember, there's some bank of pieces. You have your original inputs, and then all your deep learning pieces that have been added in. And what the optimizer will do is it will use these. It'll, at each point, it will sort them in ascending order, and that it has to redo that for each point because each point has different inputs. So it'll sort them in ascending order, and then it will use steepest descent to find the optimal pieces to be placed in the places that I've presented it. So if I say that it can have 4 pieces, then it'll pick out four pieces from the pot, which can be repeating. So there could be 4x's that would just be multiplying x by 4. That could be what we need. And for each case, it gives me an answer. So it'll give me some answer here, it'll give me some answer here, it'll give me some answer here, all the way to 100 samples. And you may be thinking now, if you know computer programming, this is going to take a while. It does take significantly longer than steepest descent, but as I mentioned, steepest descent doesn't work in this case. So what I'm doing is I'm getting an answer at each point, and I look at all of those answers and I take the mode of those answers. So what I have is that I have a function count up all of the times that answer A happened, and all the times answer B happened, and all the times answer C happened. And I look at which one happened the most. And what actually happens is that the one that happens the most, in most cases, is the correct answer. Now, it gets a little screwy when there isn't an exact answer to achieve. And so what I did was I set it up so that if it gets stuck in a hole for too long, it kicks out, says, this is the best I'm going to get. And as you saw, there are situations where that may not be true. So there are some adjustments I could make. I could add in Newton-Raphson once it gets to that hole to see if it will jump to the answer fairly quickly. But as you know, Newton-Raphson with the wrong Newton-Raphson with a bad guess is not worth the time, because it will go off to positive and negative infinity very fast, diverging, I guess, as opposed to converging on the answer. Whereas if it has a good guess, it will converge to that answer very quickly. So it's something that is a little finicky, but people people do use Newton-Raphson and steepest descent in combination, where steepest descent will sort of work as a first gear and then kick into Newton-Raphson when it gets to a point where it is a good enough guess. But that's kind of sidetracking. For now, what I'm using was working. So I'm going to try and show you what I mean by that. And so I need to pull up the actual uh, piece of code that I was working on. And so this isn't the data mining project in itself. This is just the steepest descent optimizer that is was working when I was working on it earlier. So let me see if I run this. Is it going to immediately start running? Okay. Well, I have the shell up, and so um, you're gonna see some stuff, but I'll have to adjust the screen. Okay. So there's a bunch of numbers on the screen. They won't really mean anything to you right now, but let me adjust. Also, if anyone in the audience has a suggestion for the equation we can use, I'm open to it. Essentially, what's going on is I'm creating a set of data that is a given equation that I'm thinking of on the spot. So I'm going to make it easy for the first one because I've seen it done. We're just going to go variable 1 plus variable 2 plus variable 3 plus variable 4. So that's pretty straightforward. And I'm going to run that. And it should be done. So everything's still good on the screen. Let me switch back over to this and make sure that I have the right amount of. So there's 4 pieces in the answer. And so we need to let it play around with 4 pieces. So I'm going to run it now. And what we should see is in the second little slot, there should be the first 4 digits. There we go. The first 4 digits are ones. And you can see that this happens 16 times. That's only 16% of the time. There's 100 sample. There's 100 points in the sample. So that's only 16% of the time. But 16 is the most significant number in this case. So I can run it again just to see if it will come up with a different answer. And it was coming up with a different answer because it takes a different sample every time. So it could pop up with a different answer this time. So there we go. It happened 15 times. But it still got the answer. And so what's happy about this is that it's figuring out the equation. And so there's some things I was playing around with. So I can make a different equation. What I'm changing is that the third variable is now going to be divided by the, I don't know, 7th variable. I guess that'd be the 6th variable. So it doesn't have this piece of the equation to work with. But what I was finding was that it still found the more significant pieces. So we're going to see what happens here. So I have to create the data, and so that's done. And so remember, we still have variable 1, variable 2, and variable 4 being added together. And then our fourth little piece is going to be something it doesn't have, but it should be a relatively small number. And what that means is that if it's insignificant, it still should find the other pieces. So we're going to run this and just see what happens. It could get a little screwy because it has done that in the past. Okay, so what happened here is we got 3 of the first variable and 1 of the second variable. Now this is somewhat okay because we still got 2 of the pieces we needed. We just got 3 of the first one. And so what you'll see is those will mix around a lot. But if I take one of the slots away, what I'm hoping we'll see, and I'm not making any promises, is that it will get the 3 big ones. Okay, so I guess it showed its worth to me. So we have variable 1, variable 2, and variable 4. Just like I said, the third variable is now insignificant. When we give it 3 slots, the best equation it can get is those three more significant variables. The same happens if we multiply it by a big number, or if we just multiply two of them together. So I'm going to create a new data set, and instead of dividing the third variable by the eighth variable, I'm going to multiply it by the eighth variable. So this is just a slight adjustment to the equation, but it's a big adjustment to the data because some of the data points could be significantly large. So what this means is that that third data point is very significant. So it should find that no matter what. Okay, so it didn't. I got to remember, I think I need to switch it back to having 4 slots to work with. So let me see if that changes anything. It's taking its time. Okay, so like I said, when it doesn't have all the pieces there, it's not perfect. And so this is something that possibly with some tweaking and adjustment to the steepest ascent algorithm, maybe by adding in Newton-Raphson when it does get stuck in these ruts that aren't at zero, I could tweak this so it would be more refined. But you have seen that when the answer is present, it finds the answer. So essentially what's happening is, worst case scenario, random pieces from the deep learning each generation are selected and brought into the new into the next generation. If that's the case, then eventually pieces that look like the equation that the data was created from will come into occurrence. And what this also means is that it should technically be able to approximate the data even if it's not an exact fit. And that's what I'm hoping, is that the more significant variables will show themselves. I was messing around with it earlier and it did pop up. I think that's actually what the data is up at the top there, is that there was a fourth data point in there that was insignificant. So actually we did see that happen right here. If there's a point that's insignificant, then it won't care about it if it has enough slots for all of the significant values. So this is something that could be seen with perhaps time dilation. In most cases, with most data points, time dilation is not a problem. There's no extension of length. There's no increase in mass relative to the situation. So we can neglect that effect of relativity in most cases of normal physics. And so if we had something that was trying to describe a ball flying through the air, all it would need to maybe have is like the angle that it was fired at and the velocity it was fired at, and perhaps some small term for drag. But obviously, if it had those 3 slots and those 3 pieces were available, the optimizer will find those pieces. So that's what the optimizer is doing its job, and that's why I'm happy. So what I'm gonna pull a paint window back up and switch back over to just the paint window. I'm glad I got through a demonstration without the code failing, because that happened last time. So now you guys know what the optimizer is, but and so it's not like the optimizer we had last time, where it was essentially reordering things randomly to see if it could get a better configuration. This optimizer is just finding the best situation it can find. And so obviously, like I said, it can be tweaked and it can be improved, but that's something to see if it's necessary in the future. So the way this is going to be implemented is that every generation, deep learning will create a new population of equation pieces to work with, to put on top of the equation pieces that have already been created. So essentially, the purpose of deep learning is it creates associations between variables so that more complex associations can be seen later on in later generations. And so Then each generation, the optimizer will look at the pieces it has to work with. And so, assuming that we go with my second option for the structure of this, the optimizer will be run several times with many different lengths, based off of what length it's currently at as the best length, and it will it will find the optimal equation. Once it finds the optimal equation for that length, it will simply evaluate the least squared regression at that point as a form of fitness, and the length that provided the best equation out of the optimizer will be the new best length. Also, if the if any of these temporary pieces were used in that best equation, they'll be kept around for the next generation to be used as normal input equations, because now for from similarly to the first generation, there is now this pool of inputs that can be used to be created into other associations. It's just that some of those inputs will be complex inputs created by combinations of other inputs. So that might be hard to picture, but I have given explanations of deep learning in the past. So if you need more, even you don't even have to go to where to me talking about it. I'm sure there's a lot of people who could give a quick um, summary of it on YouTube. So we have our deep learning, we have our optimizer, and so this DL, this is O. And so that's the general structure of the data mining project. And I'm fairly confident that this will be significantly more successful than um, the previous ideas that I was working with. So I've already started thinking about how this can be applied into the environment project. And so if you don't remember the environment project, because it has been a long time, our friend Jeffrey, the little robot monster thing, it kind of looks like a beetle, um, is essentially this organism that I've created in a game where the goal is to survive. If and there's points assigned with um, eating, there's points assigned with um, shooting enemies, and there's simply points assigned with exploring outside of the safety of the light area. So essentially, what I was simulating is kind of like a robot, I guess. If there's a robot with solar panels, and essentially the panel of the game in the start is this little uh, quarter circle of light. Jeffrey starts down here somewhere, and Jeffrey has to learn to survive. Now, if Jeffrey stays here too long, then his battery will never run out, but his health will, because for some reason, this robot has to eat. But bear with me. But there's little food pellets randomly spread out through the map. If Jeffrey does eat one of these food pellets, then they disappear and show up somewhere else. And what Jeffrey has is a lot of assets. Jeffrey has a flashlight he can deploy, which outside of the light will provide light so that he can identify objects when he's close to them. So if he's here and he has his flashlight on, then he'll know that this is object category blah blah blah. He won't necessarily know that it's food right at the start, but hopefully over time Jeffrey will make associations, say, "Oh, that's food. Turn, go get it." And feel better. Now, there's also random obstructions, so there's rocks in the way. These objects also pop up on his when he's in his light ring, and also there's a radar function, so he knows where objects are if he has that on within a certain radius of him. I guess I actually have it set up so if it's on the screen and he has the radar on, he knows there's something there, but he doesn't know what it is until he gets closer. And there's also enemies that will track him if he gets close and if they hit him, then he loses health very fast. But he has a little gun he can use to shoot at the enemies if he can make those associations. Now, there's some things that are very difficult to make associations on a minor scale, and some things would be trajectory. Now, so these enemies will move um, to in a step to always get closer to Jeffrey with each step. Sort of like the steepest descent. They want their distance to between them and Jeffrey to be as small as possible if they are within the screen. Now Jeffrey can sprint and get away. He can also shoot the gun at them, and if he even gets close, I was pretty lenient with the coding on that. If he even gets close, it kills them, and just like the food pellets, they pop up somewhere else. Um, and so as Jeffrey gets further away from the light in the corner, the enemies get more dense, the obstacles get more dense, but so does the food because there's more things on the screen, so the food only has so many places to go. So there is a finite amount of space. It's not procedurally generated. It's random every time, but in a sense, it's not very random how the actual areas are set up. It's just kind of like within each area, there's this many rocks that are randomly placed, and there's this many food pellets. So that's the environment project. I've tried simply having a neural network try this. Now, obviously, I've hand coded everything, so it's possible my neural network was simply not powerful enough, whereas another person's neural network probably would have done fine. But I attempted to upgrade that to a deep learning neural network, which did show some slight improvements here and there with associations, but at the same time, it was still sort of a spastic kind of randomly getting lucky situation. What I hope to do, if the data mining project is successful, as I hope it will be, is to have essentially an optimizer for Jeffrey. So this optimizer will take in all of the assets that it has in a given situation, analyze the environment, and quickly make, through use of a simulation off of what Jeffrey knows already, it will simulate the environment and then quickly optimize and say, this is what you need to do. Now, realistically, there should be a reaction time on this. And so I'm going to be playing around with that a little bit when I get around to it, of whether I can have this brain, I guess, and this optimizer running in a different program and receiving inputs from Jeffrey's body saying, hey, look, there's this obscure object that's moving towards me. What do I do? And the optimizer will have to work fast enough for it to make a quick decision and say, you need to turn here and shoot. Now, there's a lot that's going on there. It's not a split second decision. It's not a one time decision. If Jeffrey needs to turn and then shoot, that's two different things that happen over time. So there's a lot I still need to figure out. But the cool thing about this is in the end, I want the program itself to figure out how to play the game. And so this is something I've talked about a lot. But essentially what I want to do is there's going to be sort of two different departments. There's going to be the optimization department, which is sort of like the reaction. And so that's what I was talking about with Jeffrey looking at a situation, looking at his assets, and picking the best the best bang for his buck in that situation. And then there's also going to be the research department. So what I could do is essentially roll the program of of optimizing and the research program into one. This would be more realistic to a human situation because Only really one thing could be done at once, other than the subconscious things. But um, I've made it a point in, I don't know how many times I've mentioned it on this channel, but in speaking with my friends about artificial intelligence, is that human beings and organisms we've seen shouldn't be the standard, because evolution is a very slow process, and through our history of being human beings, we have evolved. Even before that, organisms evolved and slowly began to gain different processes. But it also shows you how much time it takes to improve in an evolutionary process. And I believe that it's possible that the human imagination could work faster than evolution in terms of creating a better mind. That's sort of sounding um, a little bit big-headed about my project. I'm not saying my that my AI will be anywhere close to the capabilities of the human mind, but the philosophy of of creating things in the human image is also a little bit egotistical. So, what I'm essentially thinking of doing, I guess in this case, is to possibly have two, three, maybe even more processes running at once, assuming my computer can handle it, and have um, the research department, the optimization department, all running in coherence to uh, give Jeffrey the best chance he can get. Now, obviously, there will always be failure in any terms of artificial intelligence learning. Nothing ever gets it on the first try. Second try, maybe, but nothing ever gets it on the first try. And I can assure you, in Jeffrey's case, it will take many tries over long hours of running. But what the research department is going to do is take in data and form associations. All it's going to do is take in data and form associations. So, what Jeffrey is going to be doing is, as he explores and he is gaining points from exploring around the map, by getting further and further away, he will gain a new perspective on what creates the environment he lives in. So, how often do rocks occur? How often does food occur? And so all of this will be stored in sort of a temporary long-term memory. So he won't remember things forever. That'd be pushing the boundaries a little bit, because everything has finite memory. But um, he will remember a decent bit, and be able to use that data to find associations between variables. So that's what this research department is going to do. It's essentially going to be using the data mining project that I'm developing right now to find equations that predict the dependent variables. Now, Jeffrey will know his independent variables. That's pretty important. So he will know where he sits, or like where he is, and what he can see. So those are the inputs. But through associations of where things are at one frame in time with the next frame in time, and where things are with respect to other things, like if he were here and there's a food pellet over here, but there's a rock here, he needs to know that he needs to go around the rock. He can't just go through it. So there's a lot of associations that he needs to make about specific environments. And essentially, what the research department is going to be doing is create assets for Jeffrey to use when he gets to these environments. Originally, in the environment project, I attempted to create a library of instincts, so that when Jeffrey experienced a new environment, he would log that environment, and the deep learning neural network would attempt to create instincts that would produce the highest score in that simulated environment. so that the next time he got to that environment, he would just read through the library, say, this is the environment I'm in, I better do this. But the problem with that is that finite amounts of if statements are, although somewhat intuitive, limiting. And so what I decided is that I needed to scrap that idea for a more fast-paced, more efficient idea. Because in the long run, if Jeffrey gains enough assets, he could potentially um, he could potentially figure out something before he needs to go research it. So essentially, if he figured out um, the associations uh, between the trajectory of an enemy, then perhaps if he got into a situation where there were two enemies, then he would only have to have figured out what to do for one enemy so that he knows that he can shoot one of them and then shoot the other. Now, it could be a situation where he twitches back and forth, and I don't know. I can't really predict anything, and that's what the beauty of this is that I don't know what's going to happen. I hope something good happens, but I'm just trying to create an environment so that the AI can create an environment so that Jeffrey can learn his environment to better survive in his environment. And that's why it's called the Environment Project. So, I don't have too much more to talk about on the projects as a whole. I did mention at the start of the stream that I would um, give a give the title and the band that plays the song I will be doing a cover of this weekend. That song is "I Will Follow You Into the Dark" by Death Cab for Cutie. I find that my voice is actually pretty good at not necessarily matching his pitch, but um, I'm gonna be a couple steps down just to be better in my range. But the way I tend to inflect words and whatnot are actually pretty spot on with the lead singer of Death Cab for Cutie. And at the same time, I'm trying to put my own twist on it, so it will actually be a little bit of a bluegrass kind of picking pattern on top of the normal chord progression. So you have that to look forward to, and I want to thank you guys if you've been watching this whole time. But I'm now pushing on almost an hour, so I wasn't expecting to go this long. So I want to thank you guys for watching, and I will see you on. I haven't figured out, so keep an eye on the Facebook. But I'm thinking about possibly Friday, just because I have a lot going on the weekend. So, like I said, keep an eye on the Facebook, and I will let you know. All right, thank you.